Okay, welcome. So today we're going to continue our discussion on wind. The previous discussion was developing the concept of a wind resource and calculating what the power in the wind is available to us. In today's lecture, we're really going to focus on how do we convert that mechanical energy into electrical energy, right? Because that's the whole purpose of wind turbines from the perspective of this particular class is how do we integrate renewables into the grid. So integration into the grid means you have to have electricity, so we will discuss that here. There are two main types of turbines, horizontal and vertical axis, and we'll discuss those. We're going to look at rotor blade aerodynamics, and I am going to be freely admitting to the fact that I am not aerospace or any engineer where I do not have that level of sophistication of computational fluid dynamics. I would imagine you could ask people in the structures lab, and they have a better sense of what's going on. But there is a tremendous amount of work that is being done on rotor blade aerodynamics, not only to maximize the capture of the wind, but also how to figure out how to reduce the noise. We won't get into a lot of that detail because that's more of an advanced class and it's beyond my skill set. But there is a tremendous amount of literature out there, codings, designs. It's really interesting. So I would encourage you to take a look to see if you want to get additional information there. We're going to look at how we, again, convert that mechanical energy to electricity. We're going to do things at first in terms of what's called a C sub P, or a power coefficient. Then we're going to actually do a theoretical limit. So as Professor Dvorak talked about, Carnot efficiencies, and with fuel cells, we talked about maximum theoretical efficiencies. There is maximum theoretical efficiencies with wind turbines, and so we'll discuss that in terms of the Betz limit. And then I alluded this a little bit because somebody asked a really good question about how many blades should a wind turbine be, and I said it's based on what's called the tip speed ratio, and we really need to get a little bit of material into understanding how the blades themselves will impact the quality of the wind that they see. So we'll discuss that in terms of TSR. We'll look at a few different wind turbines and some of their power curves. This gets to be fairly limited information because most of the vendor information tends to be proprietary. So to get actual information that is free to the web or freely accessible to the web is not as easy as one would think. And then we'll move on to AEP. So let's take a look at the very first electricity. This is the key thing, electricity producing wind turbine. It actually was in Cleveland, believe it or not, so it was in the United States. When you think of wind turbines, you don't necessarily think of the US as being a pioneer, but we were pioneers in terms of getting electricity generation. 12 kilowatts was the output, which doesn't seem like that much, but back in the day, that was actually quite a bit. And it really just primarily was charging batteries in the owner's basement so that they could use lights. You know, this is the late 1800s, and so if you had to burn candles or natural gas, whatever different technologies, you had a limited amount of light. And so lighting technology was available, not what we think of when we think of Edison's time, but we did have lighting available to us. And so this individual put up a very expensive turbine and some batteries, all to have electricity for light. So you get a sense of what's going on in terms of the time. If you notice, this has many, many, many blades. So this is all designed with wood slats. The turbine is long since gone, as I think the mansion perhaps maybe. But yeah, many, many blades spun at a very low speed, and wasn't really adjustable. Once you were sort of in a direction, it doesn't have the rotational ability that today's turbines do. And then just for scale purposes, that's an adult male standing next to the turbine. So you can get a sense of the scale of how big it was to produce a whopping 12 kilowatts. So lots changed since 1888 in more ways than one. Outside of the US was 1891 in Denmark. Oops, somehow I lost connection, so please pause. Interesting, sorry about that. Okay, we're back. Thank you for the notice. So we had a couple of wind turbines located next to a school in Denmark, and interestingly enough, these wind turbines are actually used to do the process of electrolysis, which is essentially to separate oxygen and water, and they actually used hydrogen for gas lights. So even though electric lights were available in this particular application, they decided to just separate the hydrogen. And you can do that effectively now. Electrolysis has been going on for probably 200 years and works exceedingly well. So this was 3 years after in the US. Looks like a much smaller scale, but again, it's hard to predict because we don't have any humans. You know, this is a one-story schoolhouse. There is a human standing here. You can see it. But it's hard to get a sense based on how far away the individual is, so appears to be smaller. Also notice a lot fewer blades than the one that was in Cleveland, and we don't think of Cleveland, Ohio as being a particularly great wind resource if you've ever been there, but depending where you are in Denmark, it tends to have pretty good wind resources. So you have much fewer blades because probably the higher average wind speed in this particular location. Now we're going to look to today and in the future. And again, we talked about 12 kilowatts. Well, in the early 80s, 75 kilowatts was available with a 19-meter rotor diameter, or blade diameter, I should say, not rotor diameter, but blade diameter for wind turbines. And then you can see evolution, and you'll notice a pretty consistent theme. The output ratings of the turbine are fairly linear and related to the wind-swept area, which is exclusively determined by the blade diameter. So right now, you can get some onshore turbines, 5 megawatts or so. Getting out to the 10 megawatts, you have very massive blade diameters, 150 meters, 500 feet from tip to tip. Not tip to tip, but actually if you could go tip to the opposite tip, if there was one there. And even beyond there, we're talking about 20 megawatt wind turbines. So massive, massive diameters. You're talking about 900 feet diameter. So have to be very, very high towers, obviously, because you don't want them impinging them on the ground. And so most likely are going to be for offshore applications, not necessarily onshore. But now you're getting to decent power densities in a single generator. 20 megawatts, does that sound like a big generator? From a wind turbine's perspective, perhaps, but from an electric generating perspective, that's not that big. Actually, that's probably on the smaller size. Maine Independence Station has 3 generating units, and each one is about 150 to 180 megawatts, and those plants are 20 years old. So nuclear power plants, if you go to Connecticut, they have a 1,300 megawatt generator, Seabrook 1,300 megawatt generators there. So, and those have been around for 40 plus years. Yes, sir.
But in theory, they wouldn't only have one of these, right? They would probably have them in like a line or something, so it would be equating more than just 20
Yeah.
megawatts.
Yeah, so the comment or question is, they'd have more than one of these? Yes, you would not put, just a single turbine because of the costs of a single turbine would be expensive. But the reason why I was saying that is, again, we have to consider renewable energies, and not only its reduction on use of fossil fuels and reduction of CO2, but also it does have some pretty dramatic effects on using up, resources, land, right? So if we have 10 turbines to produce 200 megawatts, that's a pretty sizable land area that's not going to be available for anything in the future. And so how do we combine farming or whatever? I mean, you can farm underneath wind turbines, perhaps, if you're willing to deal with some of the noise, but maybe you aren't. So I don't know, at least in North America, where a lot of that is happening. Where transmission towers, you do find farms underneath there, but pretty limited in Maine. And yeah, so there are impacts on it, but yes, you would have multiple turbines at one farm. So let's get into the two different types, horizontal access and vertical access. If you always get confused, I try to teach this to my 4-year-old. Look at the H. That'll tell you the orientation. So if you look at the H, that tells you that it is parallel with the ground. So a horizontal access turbine is here, and a vertical access turbine is the opposite. By far, the most common design is the horizontal access turbine. Let me move this up just a little bit more. And really, it has to do with the fact that you're getting up to higher wind speeds. I've got some advantages and disadvantages, but it's exactly the same concept, right? You have some sort of blade structure, and here, 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 and here, and it is rotating some sort of a shaft. This is the horizontal axis. This is the vertical axis. So the shaft is what we're talking about in terms of if it's vertical or horizontal axis. And then you have usually a gearbox and your generators here. You have the same concept here with a gearbox, and then that drives onto the side a generator that's connected. And that's pretty much the only two designs that you have, major designs that you have for wind turbines. Since they're not that common, put up some examples of it, and you can see the Savonius is sort of an artist's rendition because there aren't a lot of good practical ones out there. So it basically is just an airfoil trying to capture wind. With a Darius uses a curved blade design that goes from the base to the top. A little hard to see, but what makes the vertical axis wind turbine so cheap is all the weight is at the ground level. So when you erect these wind turbines, you need to think about how expensive is it to erect it. Well, if you have the heaviest piece of machinery is at the ground, to erect it you need a small crane, right? And then you can almost have a tall crane, but doesn't have to have the capacity to actually be able to erect this thing. This also actually has, and it's very difficult to see unless you probably aren't looking at the slides, you actually have guy wires, right? And so the foundation design can be a lot more simple because if it's a horizontal axis turbine, it has to be able to account for all the forces that are trying to essentially tip the tower over. Where in this case, all you have to do is guy it out, and because of the mechanical advantage you have with the guy wires, it's a much more basic and simple foundation design. So it has to support the weight. Obviously, you don't want it moving around and cracking, but a very, very simple design relative to our horizontal axis. This is a combination one that has the Savonius and Darius, and again, this is one that's a research project. I don't know any of them that are actually implemented. But it's got the Savonius and the Darius. So the Savonius here in the center, whoops, captures wind effectively when it's low speed wind. So lots and lots of wind can rush into these areas here. And then that provides the motive force to rotate the turbine. At the higher speeds, you actually have the concept of lift that's getting that to rotate. So you're actually spaced out more, but that's because as the wind is impinging upon the blades, the wind's going to slow down, right? Energy is removed as you get those blades to rotate. So there's a much more spacing, so these blades actually operate at a much higher efficiency at high wind speeds. They're almost non-effective at low wind speeds. So the combination of these two actually gives you a reasonably good low wind speed cut-in and higher efficiencies at higher wind speeds. Okay? More power is available to you at high wind speeds, so it would make sense to maximize as much efficiency as possible. But if you don't have high wind speeds, you would still like to produce power if possible. So a couple of advantages, and we talked about that. The weight is on the ground, so makes it easier for construction. There's some gravitational stresses, and if you think about the movement of the Earth, you get some cyclical gravitational stresses with the moon. How realistic is that? Again, that's a little bit beyond my pay grade, but you get the sense that there is some analysis that's being done. And then the other nice advantage is they self-orient themselves. They're always rotating, so whatever direction the wind is coming from, they're always going to capture that. So they don't have to rotate, they're just going to always be capturing. So it makes the design a little more simplistic because you don't have to worry about having another rotational aspect of this equipment to rotate to capture the wind. It has mechanical resonances, that could be an issue. You can have a severe aerodynamic load as you rotate. So when you're in the wind and when you're not in the wind, you have a massive amount of twist that's occurring because there's so much more power occurring on the front and on the back end that you can actually get some twisting happening in your shaft designs. You don't have to use guide towers, but it's much cheaper to do it. So there's a practical limit as to how far up you can go, all right? And that's because if you think about a tower, right? You have a tower coming down you have to make sure your guys are far enough outside here so as these blades are rotating along, they won't hit onto the guy wires. So you have to angle out pretty far, which is not a big deal, right? You can get to, extreme lengths, but the problem is you have to lease the land that these turbines are located on. So if you're getting to massive, great distances, then there's additional costs for you to lease that land. So, and most large, I would say, you could almost correct us to say all large machines. I don't think anything over 10 kilowatt is not a horizontal axis. Here's the tried and true horizontal axis that you've seen. So again, the reason why it's horizontal axis is because the shaft of the generator, yes sir?
Do those guide wires limit the density for vertical, like, because you can't put them, the wires are literally in the way of where you could place the other ones?
Yeah, so the question is, do the guy wires impact the location of the other turbines? Absolutely, but you could rotate, right, where the guy wires are located, because you just have to space them 120 degrees. So you could actually rotate them, and you could get them almost, on top of each other as long as they're rotated correctly. So they don't actually have to be next to each other. You can rotate them, so as long as they don't impinge upon other turbines, then you should be fine. So I've never seen a wind farm designed with all the vertical axis wind turbines. There is perhaps one out there that probably is a design consideration. But again, as long as you locate the guys 120 degrees out of phase or 120 degrees from each other, it shouldn't make a difference at all. So good question. So horizontal axis, the key things here are inside this box, and this box is called nacelle. This is sort of a term that has come along because it's where, if you look at airplanes, that's where the engine components are located. So they figured in a wind turbine, maybe that's where the engine, quote unquote, is. Really, it's the generator and the gearbox and any auxiliaries that you need. And you have your actual hub that's connected at that location. That's a completely separate assembly that you can detach and reattach, and that's mainly for construction. It's easiest to erect the nacelle first because it's the heaviest weight, and then you erect the hub with the blades on after that. And usually what you do is you put one blade on, or maybe two blades depending on who you talk to, and then you tilt it up, and then you put the third blade on, and you do that sort of at a lower level, and then you just basically attach it to the front of the nacelle. The rotor diameter makes sense, right? So whatever the rotor, the radius of the rotor is, you just double it, and that essentially gets you this diameter. Inside this area here, this is your windswept area. That's your pi r squared. That's where you're going to actually be extracting power from the grid, or from the wind. Your electricals all come down inside the tower and go out underground. And if you haven't thought about it, you have to have electricity coming out of there. And you don't want wires, to be tacked onto the side of your turbine going out, mainly because you've got blades spinning and you don't know where those directions are going to be. So, this is kind of a cartoon showing you that it's half the height, but they usually go much lower than that. So you wouldn't want your blades to be hitting upon your electrical. So usually what happens you have at the base of your wind turbine, and again, this is a little bit more North American specific, you have a pad-mounted transformer and a switch. All that stuff is all underground. So you've got some voltages, and it could be a transformer there, or it doesn't need to be, but you could have lots of low voltage cable or a little bit of medium voltage cable, and then it goes out, and then you run at least a couple 100 feet away, and then you would pop up above ground and then go overhead, because overhead construction for interconnecting electrical systems is much, much cheaper than underground system. Mars Hill is all underground. I was involved with that, but I was not involved with the decision as to why everything is underground. But it's all underground, so their entire electrical system, their collection system is what it's called, it's underground. So it looks a little nicer up there. So you have your foundation, and the foundation design is really a very interesting thing. If you ever have a chance to see one go in, it's a lot of concrete, a lot of rebar, and they actually have to bolt the base to the concrete here, right? And the way that they do it is, if you think about the torque that they have to do, it's, many, many, many foot-pounds. I have no idea what they do. So actually they have equipment that uses like a hydraulic press that actually will press the bearing down, or the assembly down, and then you just screw the nut down till it's just hand tight essentially, and then we'll remove this hydraulic press, and it's like torqued to whatever the recommendations are. So it's quite a torquing process, and they're torqued so tight that they just don't, you don't have to worry about undoing them. Do they actually weld them in place? I don't know, because I don't think anybody could use a wrench to twist them off. I just don't think it's practical. Other applications that I've seen, what they do is they heat them up. And so in really big turbine applications, they actually have something called bolt heaters, where they put a heater directly in the center of the bolt, and they heat the bolt up, and its expansion and contraction is different than the nut. And so then you can take the nut off. Otherwise, if you just did it with a wrench or whatever, even if you had miles of pipe wrench, you wouldn't get it off. You would probably snap the bolt or whatever. So it's a real process in getting those erected. Really fascinating if you can ever get to see it. Let's talk about the blade or blades. The original design is, let's just make it look like an airplane wing. That works for airplanes, right? Obviously, there's some energy that's being captured because the airplane is in the air. It's not crashing to the ground. And that was a good concept because there had been a fair amount of work to come up with the aerodynamics to have very efficient blade design. Well, there's only one problem. Here, airplanes are translational. They basically go in a straight line, right? Turbines are always rotating. So what you're trying to do with an airplane is to keep it going in a straight line and to have lift. With a turbine, you're also getting the blades to operate in the concept of lift, but you're wanting to convert that to rotation, not lift, in the true sense of trying to actually elevate something. So the actual blade design is far different than what you would see on an airplane wing. And a lot of that has to do with, as you get closer to the tip, your wind speed is the same, but your speed relative to the ground, right? If you were to think about, the rotational speed, well, if a hub is rotating at, let's say, 30 meters per second, at the tip it's also rotating at 30 meters per second, but compared to the ground level, it might be at 300-400 miles an hour, right? So they have to have a very different design at the tips than they do where they connect into the hub. So quite a bit of design that goes in, and that's why if you see the blade like it is, there's a little bit of twist and it feathers out before it kind of comes back to a point. So the concept of lift is you force the wind over the wing to go at a faster rate than the wind below. You make it go at a longer distance, essentially, so it has to be back at the same point. So you have basically less density because of the further distance that the air has to travel, and you actually get the concept of lift. That applies here, but you're lifting sort of in the left to right direction, okay, if you were to rotate in a counterclockwise direction. This is just some of the terminology you'll see where, again, you do computational fluid dynamics, where you have the wind, and again, you've got a shorter distance going under than over, and then that gives you the lift. And then some of the other plots here where you have angle of attack, so you can adjust the amount of lift that the wing or the blade is going to experience by adjusting this angle of attack. You can increase it or decrease it depending on your perspective, and you get a higher coefficient of lift. Wind turbines are designed so that in their normal position, they have a maximum angle of attack to get maximum capture of wind, okay? So you're not adjusting the blade while it's at a low wind speed. You're only adjusting the blade when the wind speeds are too high. You actually want to shave some of the wind. You don't want to capture that much energy, because once you've exceeded the generator output, at that point you're not generating enough induced torque to slow the turbine down. So it's going to continue to speed up. So at that point, the only way to do it is there's so much power in the wind, is start to shed some of that energy so that you don't capture it, so you don't overload or overcapacity your generator. Let's talk about that coefficient of performance now. So we looked at this slide, or similar slide like this last class, but let's actually apply it now to power in the wind. So we have two velocities. We have an upstream and a downstream. And you'll notice it's a funneling effect, essentially. The reason why it's a smaller area here is it's a much higher wind speed on this side than on this side, so it expands out. over a greater area because you've got, a certain amount of particles at a slower speed, so it basically has a different density there. So what we're also assuming is the mass flow rate between the upstream and downstream velocities are going to have a constant mass flow rate. So the amount of air moving, okay, not the speeds, but the amount of air that's being moved is the same. And that hopefully helps you understand why that's such a bigger area, because it's at a slower speed, but you still need to have the same amount of mass. You need more room to do that. So our base equation, right, if you recall, and we're not even going to focus on which average we're going to be using, it's just 1/2 rho area times the cubic of the velocity. But that doesn't include the fact that the turbine is not going to be able to extract every ounce of energy out of the wind. So the way that we do that is we put this power coefficient in between or inside the equation. And that coefficient's always going to be between 0 and 1, and it's going to depend on wind speed as well as the speed of the turbine. The area, right, is pi r squared, or pi d squared over 4, works the same. And the velocity that we're talking about here, we would like to do it in terms of upstream or undisturbed wind velocity, because the downstream wind velocity is dependent upon how much power has been extracted. So that's going to be a somewhat unknown, but if I have an anemometer device that's monitoring the upspeed wind, then I can predict how much power up I should be, or I should receive. So that's why we use things in terms of upstream wind velocity. Another really interesting thing is your cost of your wind turbine is about proportional to the blade diameter. But remember, the power output is based on the cubic of the wind, right? So if I can increase the blade diameter, and it costs, it's a fairly linear increase to get that, I can pick up or extract a lot more power with bigger blade diameter. So you're seeing more and more effort to get larger and larger blade diameters. At some point, we can't get much larger because we have to erect towers that are so high it's not practical. But you see much, much taller blades than even 10 years ago, or longer blades. So let's take a look again at that C sub P, that power coefficient. So if we think about extracting energy, we would extract every ounce of energy that's in the wind when the downstream wind is there's no wind speed, right? If you've got upstream wind, it's got energy. If there's no downstream wind, then you've extracted every ounce of energy. There's no more velocity in it. All that kinetic energy has been converted over. Well, that doesn't make any sense, because at that point, your downstream wind, whatever that was there, that was moving air particles out of the way, we'll say, you need energy now to move those air particles out of the way. So you don't want to take every ounce of energy, because for the next time, the upstream wind is also going to be responsible for pushing those particles out of the way. Well, we don't want the velocity of the downstream wind to be zero, to have no net difference, because if they're the same as upstream or downstream, then we didn't capture any power. So those are our two extremes, right? Zero velocity or the same velocity as our upstream. So this gentleman, Albert Betz, in 1919, started thinking about and said, what is the way to do this calculation? So let's take a look at our mass flow rate again. So it's that 1/2 mv squared, but I'm going to do it now as the difference in speed that's dropped between the two. So the power I'm extracting is going to be predicated on the change in velocity from upstream to downstream. And so it's still, again, it's 1/2 times the mass flow rate. So go back to that rho A V equation that we had, right? So we have this equation. Here's our mass flow rate written as what we had learned from the last class. And then we're going to go ahead now and just take an average. We're going to assume that the velocity is the average between the two, a reasonable assumption that we can go ahead and take into account. So our mass flow rate is going to be our air density times the area times the average of those two velocities. So now what we can do is we can figure out how we actually we'll calculate what the power is by substituting in our mass flow rate equation and the differences of velocity. And our equation to calculate our maximum efficiency will be using this, except we've got some additional v squareds in there, and these equations are not super useful. What would be useful is to figure out some ratio of upstream to downstream, downstream to upstream wind to figure out how much wind speed, or how fast the wind has dropped, or what value the wind has dropped to. And then we can use that to calculate what the maximum theoretical efficiency is. So once we know how much the best case scenario is to drop the speed of the wind, then we can calculate what the maximum efficiency is going to be. So we're going to define lambda to be that ratio that we're looking at. And then we're going to substitute into our equation our lambda, so that now all we have is lambda and our velocity, our upstream velocity. So we've gotten rid of essentially the downstream velocity and written it as a ratio between the two. So that's all we've done, is made a couple substitutions. Now we're going to do a little bit of fancy-dancy algebra to simplify our work, and we're going to focus on, whoops, let me go back to here. We are going to focus on this one and then multiply it back in at the end. So our upstream velocity times our downstream to upstream velocity ratio times divided by 2, and then just multiply that out. We're going to end up with a simplification of our equation that is here. Then that gets placed back into here, and this kind of looks like our original equation, right, for calculating power in the wind. But the original power in the wind part was only this part. And as we mentioned, we want to figure out how much energy is captured. The remaining term that we have, which is here, is the power coefficient. All right? So now we have it written in terms of actual energy being captured and converted into electrical energy. So now we can actually figure out what our value needs to be. So our power coefficient is we've defined it here, and then we're going to expand it out just by foiling it and multiplying it out. And if you remember from Calc 1, when you did optimization, how do you know when you reached a maximum or a minimum point? You take the derivative and set it equal to 0, right? Because whenever the slope of the line, if the slope is 0 or 0, right, we've either reached a max or a min point. So we can take the first derivative of this equation, set it equal to 0, and then solve for our lambda, and then that should tell us what the maximum or what the best speed reduction is. So our ratio should be about a third. Reducing the upstream wind to the downstream wind by a third is going to be when we achieve maximum rotor efficiency. So now we have lambda equal to 1/3. We're going to plug that in to our coefficient of performance. And here's something you need to highlight. Because the maximum possible theoretical limit, you cannot achieve more than this level of efficiency for extracting energy, is 59.3%. You'll never get to 60% and extract that much power out of the wind. You can't get beyond there. Okay? So when you think about what was happening in thermodynamics, where you just try to increase temperatures or decrease temperatures, do a combination, you can get the temperature difference between the two higher, and you can get higher and higher efficiencies. That doesn't work here. Okay? So you're going to see that the maximum efficiency you're ever going to get is 60%. That's why I said turbines today have typical efficiencies of 40 to 45%. So to get to those higher level of efficiencies, it's not practical and actually not even viable. And this is called Betz' law, or the Betz efficiency, named after the person who came up with this concept. So this is kind of a summarization, right, which is downstream velocity is 2/3 of the upstream velocity. And then the corresponding C sub P, where you have maximum coefficient, is almost 60%, 59.26%. Here also shows you as, let me go up a little bit more. So remember, this term here is equal to lambda. So as my lambda increases, right, so I start off at 0, so essentially half the energy would be converted to electricity, and then the other half is responsible for pushing the old air particles out of the way. That would be at, trying to extract 100% of the wind power. Down to there's no difference, right, and obviously we're not extracting zero power. Or we're getting zero power out. Right at this point, where the ratio, right, is 1/3, is where you get 59%. That's maximum efficiency. So that's theoretically the maximum is 59%. But how does that relate to real-world practical turbines? Well, we've already talked about the wind. We want to extract energy, and when we do, it slows it down. Well, if we have blades that are spinning at very high rates of speed, or blades are coming by fast enough so that the wind that was there before, the air particles before, are still slowed down and still haven't had a chance to sort of get out of the way, you're going to reduce efficiency. So this idea of this tip speed ratio is a control parameter where you actually are controlling the turbine based on what the rotor tip speed is, how fast the rotor tip speed is, which is pretty easy calculation, right? Once you know what the angular velocity is, you multiply by the distance of the length of the rotor, and you have the rotor tip speed relative to ground. And then you divide by the wind speed, and that gives you your tip speed ratio. And here is the formula to do it in terms of your diameter, your wind speed, and your RPM of your blades. So I think this figure here crystallizes why would we run with more than one blade, more than two blade, more than three blades. It's just based on when can you capture maximum power. If I have a single blade design here, I can spin that at very, very high tip speeds, right? My RPM is very high relative to the wind speed because I have to go at a high rate. I can go at a high rate because it takes a long time for that one blade to get back to come to the air that has been had energy extracted to it. I go to 2, and you notice 2 does not have quite the same level of tip speed ratio, but it's a little bit better than 3, right? And then we start getting into our vertical axis, and as I mentioned before, look at our turbine with many, many blades. That has its highest efficiency at extremely low tip speeds, because if you run too fast, the air that was there pushing the wind it's still in the way, essentially. It still hasn't moved on, if that's the right term. So why go with a 3-blade design? There's a couple reasons. The first reason is it has the closest efficiency to maximum out of all the designs, right? But that's expensive. 3 blades is a lot more expensive than 2 blades, which is going to be more expensive than 1. So that's part of the reason. So you could say, well, if I would just go with 2 blades, I could potentially save some money. Well, the problem is if I have a tower with a blade here and a blade here, the power that is affecting here is much stronger than the power that's here. And so what would happen is if you were to look at a profile view, if you just use 2 blades, your forces with a lot of wind would be tipping the nacelle in that direction because of the massive amount of force that's being applied to the tip. So with 2-blade or with a 3-blade design, you have 2 forces to balance out the maximum force that you have there. So it has the best case characteristics in terms of longer lasting design, because having a tower that does this, because it's going to be tilting, it's very hard on the blades, it's hard on the bearings, there's a lot of issues with maintenance like that, where this one doesn't have the same set of issues. This one over here doesn't have the same set of issues with torque because, again, you have so many blades it doesn't really matter. But that's why we have standardized on 3 blades. You do see on occasion where you'll see 2-blade ones, but they're not that common. Those would be like very high wind speed applications, and I've never personally seen a single one. So that hopefully answers the question from the previous class as to why why not go with more blades or less blades for that matter? It's really maximizing efficiency, but also the forces on the gearbox and equipment there. So let's take a look at an example, a Riva Multibird 5 megawatt machine. It's going to produce 5 megawatts at a pretty high rate of wind speed, so 12 meters per second. Its rotor diameter is 116 meters, and its rated speed as to when it puts out 5 megawatts is only 14.8 RPM. So based on the fact that it's running at 14.8 RPM, and we know what the rotor diameter is, we can calculate what the tip speed ratio is going to be at a specific wind speed. And when we know that, we can actually calculate what our power coefficient is going to be. So, first thing we're going to do is calculate our area. So our area of our turbine is 10,568 square meters. Our tip speed ratio is just that equation, RPM times pi over d, divided by 60 times the velocity that it's rated at. So the tip speed ratio is 7.49. And how does that compare to here? Well, if you take a look, right, 7.49 is pretty darn close to where you get your maximum efficiency, right, for a 3-blade design. So most 3-blade turbines are going to be right in that 7-ish, 7.5-ish range, because that's where maximum efficiency is going to be operated at. And again, you're trying to design systems to get maximum efficiency, so you can see why, the maximum theoretical efficiency is most likely where it's going to be where you're going to calculate the best case efficiency there. So here's our power coefficient. So we're going to back calculate, because we know what the power is at 12 meters per second, all right? It's 5 megawatts, and we know the area, and we know rho. We should be able to calculate the coefficient, the power coefficient, Faley efficiency by using that value. So this tells you 44.6%. Remember what I told you about efficiency? So between 40 and 45%, this is at just under 45%, and this is its maximum efficiency scenario. So you're not going to find much higher numbers than this 44.6%. This is pretty standard. Let's compare that to our vertical axis wind turbines. So we have a 4-meter blade diameter. The height of this is 5.6 meters, so what is that, 18 feet or so, 19 feet? The blade diameter is, blade number, not blade diameter, blade number is 4. Cut-in wind speed is when it actually starts to produce power. So until you get to a certain speed, it doesn't make sense to really turn the system on, because there's just not enough power in the wind to make it worthwhile. Why have all the equipment operating and trying to get power out unless you have a certain minimum? So somewhere on the system you have to have an anemometer to say, I have at least 2.5 meters per second wind, so turn on. Yes, sir?
What does it mean to turn on the system? Like, it's generating power.
Yep. So essentially when your system is being turned on, you essentially are starting to generate electricity and are interconnecting to the grid. If your speed is below a cut-in speed for a long enough period of time, at that point, it's still going to be, the electronics and the controls are going to be energized, but your generator is not going to be energized. You're going to kind of let the system freely spin so that you're not putting a lot of load on the system, as long as it doesn't overspin, and it shouldn't, because the wind is so low. You're really going to try to minimize, because at that point, you're actually taking power from the grid, and you have to pay for that electricity. So you try to have as few pieces of equipment running as possible, because you just want to try to not use the energy unless you absolutely have to. So you don't officially connect it to the grid and keep it connected until you hit your cut-in speed for a certain period of time. Okay, good question. Look at the RPM here, much higher RPM, right? The other one was, what was it, 14.8? This is 180, so 10 times greater. If the power in the wind is too great, we already talked about this, there isn't enough induced torque provided from the generator to slow the unit down as it continues to cut, as it continues to do that. So at that point, you are having so much power that you actually can't maintain a safe system. So at that point, you would shut it down, because you cannot slow it down enough, so you might let it freely spin. More than likely, you would try to put a brake on it and lock it in position and just keep it, because at that point, if it's spinning, you just can't control it. So you might as well slow it down and stop it in position to do that. Again, this has to be sustained wind speed, so if you have a gust, there's not enough momentum. I mean, it takes enough time for momentum to build up to get these things to accelerate. These are massive systems with high levels of inertia, so you need a lot of energy to get them to accelerate. But if you have long sustained, you could do that. So it'll cut out at 15 meters per second, which is 50 miles an hour. That's a pretty good wind. And it can survive up to about 190 miles per hour. Anything beyond that, and then, who knows what happens to the turbine blades. They go flying, apparently. Here's another one. This is Gamesa. And you'll notice with the smaller blade diameters, you have the smaller output. When you get to the higher ones, you get the higher. You'll notice that this unit here can produce 2 megawatts at 60 meters blade diameter, but be careful, that's in very, very high wind conditions. So this is designed to maximize its efficiency at high wind speeds, okay? So its blade design is going to be a little different than it would be for the G8X that's 100 meters, for example. So you can take a look at some of the rotor diameters here. So our 80 meter, 87, 90, these are all for the 2 megawatt units. Here's inside the nacelle. So one of the things that may or may not be obvious to us is when you have a generator, your generator here, and let's just draw this as a box or a circle that has an output here. And this has to connect to a system that's operating at 60 hertz. So if it's spinning, it's going to be generating AC. You would like that to be as close or exactly at 60 hertz as possible. If it's spinning at 15 RPM, that's slower spinning than what a hydro facility has. And hydro facilities need massively large units because of the torque. The power equals torque times omega. So power equals torque times omega. If you're trying to put out 5 megawatts and you're spinning at the equivalent of 15 RPM, you got massive amounts of torque on that machine, okay? If your RPM now is 3,600 RPM, you can put the same 5 megawatts out, but you need a lot less torque. So you put a gearbox in there to have the nacelle or the tower of the hub running at 15 RPM, but the generator themselves are running close to 3,600 RPM or 1,800 RPM. So you can make them far, far smaller in size, much, much smaller. And so most units will have gearboxes. In fact, all the ones I have had gearboxes. That's probably the most maintenance that needs to be done on them, okay? So fairly elegant pieces of equipment, again, but their whole purpose in life is to transfer the energy, 5 megawatts, and step it up in speed. This one does a pretty good job showing you some of the electrical cabinets here. And then also in this particular unit, the transformer that steps the voltage up, because the generator might be generating voltage at 690 volts, 750 volts AC, but it's going to actually connect to the grid at maybe 35,000 volts. So the way General Electric does it is they just run lots of low voltage cable down to the bottom of the tower. If you can put the transformer up at the top of the tower, you can run cheaper cables down to the bottom. The downside is you got a transformer at potentially 300 feet in the air, so changing that out is going to be more of a task than if you have a transformer at ground level. So getting that up there is not easy. Also, you got to keep in mind that the transformer should be able to come up through the tower in the center and then be set in place. All that maintenance, unless it's a major piece of equipment, maybe the generator, all that stuff has to be brought up through the tower. You're not going to use a helicopter and take off the covering. I mean, this is not a simple task to do at 200-300 feet in the air. So a lot of that stuff is done through the tower. So you've got hoists and cranes, and everything is positioned just right so that you can actually move your equipment through. Not in all cases, but as many cases as possible.
What about direct drive wind turbines? Do they use those a lot?
Great question. So if I look here, let me skip ahead a little bit. You do have direct drive technology. The downside of direct drive technology is your generator, which is here, is going to be putting out a frequency, whatever the freewheeling frequency is, and that means you have to run all your power through power electronics. Whereas if you don't have to run, and the GE turbines, they direct connect their generator output, most of their power goes directly to the grid, but that's not it's not practical with direct drive. So you need big power electronics that aren't as efficient as direct connections, and are expensive to operate and maintain. So you do see a few, but they're not nearly as popular as the gearbox getting it close to speed.
So where do you use them? On like like if you had a big commercial facility and you wanted your own wind turbine, would you use them there as opposed to
What's that?
direct drive?
No, you can use them connecting them to 60 hertz. It's just that they're not as efficient or as effective as just doing one with a gearbox. So it's not any other reason other than cost and maintenance. Because maintenance on a gearbox, it is an issue, it is a concern, but it's still more efficient and cheaper than using direct drive. So let's go back. This shows you the generator, and pretty standard generator. You would have an excitation system on the rotor. If you want to learn more about excitation, you can come see me and I can talk to you about that after the fact. It's not really the scope, but essentially you have magnetic fields interacting with each other, and then that's how you produce or you convert mechanical energy to electrical energy. It's all done through magnetic fields. And then here's the cover, and like you said, you have the hub and the cone, and then you also have some measurement to actually get a sense of what the wind speed is and the wind direction. Because, and I don't know if you noticed this, but if I go back a couple slides, you can see it here. If you look closely, you can see sort of a geared something or other there at the base, right? Well, the reason why you have that is because you have to orient these. They have to be rotated physically to be in the prevailing wind direction. So literally, you have a device that turns the entire nacelle to be directly in line with the wind direction. So that's the advantage, the disadvantage of what's called an upstream horizontal axis wind turbine is it has to be oriented in place. If it's a downstream one, it auto-orients. The downside of that is now you have the tower slowing down the wind on a portion of the blades impacting it. So again, most of the commercial turbines that are larger scale, they almost always have upstream and they just rotate like this. So it actually will position itself to do it. And it takes a while because it's not something you want to be changing constantly, but it does work. So that's how we orient the wind, and then again, you can get a sense of scale. You can get a look at the adult male, I believe it's a male, that is there. And then the standard stuff, right, you have to have warning lights for FAA. I think anything in the US is over 200 feet has to have a beacon at the top that's constantly blinking. You also want to make sure you have this part here, which is a lightning rod, lightning arrestor to protect some of the electronics. But the blades themselves also have some equipment there that's designed to take a lightning hit because they're made of fiberglass, but you still want to direct some of that energy away from the devices, and so you actually can do that. It works pretty well. Here's another figure that talks a little bit more about cut-in and cut-out speed. So again, don't bother cutting in anything around 5 meters per second. There just isn't enough power in the wind. If you look at watts per meter squared calculation, when the wind speed is 5 meters per second, there's not a ton considering the fact that you actually have to do the auxiliaries, transformers, excitation system, all those consume power. So you have to have enough power in the wind to overcome those losses. So this unit doesn't even turn on until you hit 5. At 15 meters per second, it's going to continue to ramp up, and you'll notice this curve is an exponential curve. This is that cubic of velocity, right? So you're getting slight changes in efficiency, but not that dramatic. And the reason being is because, as I mentioned, the angle of attack for the blades is set up to do maximum capture of wind. Once you hit 15 meters per second, does the wind speed or the power in the wind go down? If the wind speed continues to go up, right, that would be that case. But you cannot put out more than 1,800 or 1,750 kilowatts out of the generator So if you try to continue to go over that, you're going to burn up the generator. So at that point, you start to feather the blades, so you start spilling the wind. So you now are twisting or turning the blades to actually not have maximum angle of attack to shed some of the wind. And that'll continue on until this particular unit hits about 25 meters per second. And anything beyond 25 meters per second, you really got to put this turbine and slow it down and stop it for survivability. So you literally have to put the brakes on and lock it in position to prevent it from rotating. So this is just sort of a nicer figure. I think this is from a GE catalog, which tells you the 3 different regions. Region 1, which is, don't even bother running, and it shows you the yellow line, which shows you how much power is in the wind. Once we get to a sufficient speed, we can actually get enough to cover our auxiliaries. So we're going to turn on and just maintain maximum energy capture. And then when we hit region 3, we're going to actually go ahead and start to shave or get rid of the wind that we have. So we're going to shed it, not shave it, but shed it. And at that point, our power stays constant. Our rotor RPM is also going to stay constant as well. We're not going to increase it too much, although if we increase it, we actually would get better tip speed ratios, but this particular unit, that's how it works. And then again, after a certain speed, it's not even in an operating region. It's basically surviving at that point, so we would shut her down. Last couple slides is how do you calculate annual energy production? Well, if it's velocity specific, right? So we already looked at a Rayleigh distribution, which has characteristics, so we can't just use the average. So we use our probability density function, which we get to tell me how many hours at a specific velocity. And then the turbine will tell me how much power it can produce at that velocity. And then we sum those together, and that'll give us our total energy production over the course of a year. So here's an example where we have actually calculated what the hours of operation are in a year, then what the output turbine power would be. So you can see at 14 meters per second, we hit 1740 kilowatts, which is the rating of this machine. And then the number of hours that we have multiplied by the energy will tell you how many megawatt hours you have. This has an average or median wind speed of 6.6 meters per second. So you can take a look at the Rayleigh and see if you would get that power output. Here's it in more of a nice graph form. Now I've got my total energy, which I am producing. Keep in mind though that the turbine is rated for 1740 kilowatts. So if it ran at 1740 kilowatts full out for the entire year, as opposed to what it produces, its capacity factor is 0.24, which is pretty standard. So for renewable energy, they tend to have a fairly low capacity factor because when is the wind blowing at 15 or 14 meters per second? If it's in a steady offshore application, okay, maybe you have higher capacity factors, but onshore they tend to vary quite a bit. So that's why we want to locate stuff. Not only we have high wind speeds, high average wind speeds, but consistently high average wind speeds. So you get 6 meters, 7 meters per second, 90% of the year. And it doesn't go up from 6 meters per second to 12 meters per second and keep bouncing around because that's very difficult for the turbine to capture that. But if it could stay at 7 meters per second for long periods of time, 8 meters per second for long periods of time, that's a better site than one that has a higher average wind speed, but it's constantly bouncing up and down because the turbine just can't respond that quickly to those changes. So that's kind of where we come up with capacity factors. And this is where fossil fuels, or anytime you have a system that has a fuel source, tends to have much, much higher capacity factors than renewable energies. So in the 10s or 20% for renewables, that's the best case you can do. PV is even worse, right? Because you might get peak sun 3-4 hours a day. So that's if you've got 1 megawatt PV array or PV system that can do 1 megawatt, it can only do that for 2 hours a day. And that's assuming peak sun. What about if it's cloudy? So it really changes the equation quite a bit when you look at renewables. Where nuclear plants, right, we looked at nuclear plants, those are running at 90%. Other factors that affect capacity factor are not just fuel and is the sun out, is the wind blowing, but the other a discussion point is do we actually have demand for our power? If we're selling power at 12 cents a kilowatt hour, but I can buy it down the road from ABC Energy at 7, then my capacity factor is going to suffer because the utilities are obligated to buy lower cost of energy power from, just to keep the consumers happy. So it would be nice to do renewables, and you can opt in. There are opportunities to get, all renewable power, but it's not always going to be the case that that's how it works out. So capacity factors on renewables tend to be lower, higher on conventional technologies, especially ones that are low cost. Old coal plants are that way, but now because natural gas has gone cheaper and you get combined cycle, those you're starting to see more and more. But nuclear, at least for the horizon, it's pretty cheap to run them at 100%. So, those will probably dominate for a long period of time. So I think that was my last slide. Yes, it is. So thank you very much. We have one more discussion on wind, which will be on Tuesday, and then Professor Dvorak will jump back in. I can't remember the exact topic, but you should have a quiz that's going to be up. I think it's up already today on wind. So you'll have that, and then you will probably see me one more time this semester, and we'll do actual distributed generation and how this all interconnects in. And we will go from there. So next class on wind is the downsides of wind and wind farms. Question?
Well, actually, might answer. So I've heard a lot of people say that wind isn't really worth it. I guess it doesn't pay for itself.
Yeah, so the comment is wind worth it? I would disagree with what people say, because people would not be putting up wind turbines unless they thought they could make money. So part of it was there's incentives, right? Federal incentives to go ahead and do that. Would it make it on its own? No, because fossil fuels are relatively cheap, right? But it's the same thing as electric cars and other technologies. You need early adopters to kind of get the technologies to be cheaper. So, once we start to figure out how to do more offshore stuff, I think that's where you're going to get to be lower costs, especially if we can figure out how to support them at a cheaper, the foundation designs, or if they're going to be floating. There's just a lot of work that needs to be done. But almost any renewable energy doesn't fly if it's just taken on its face value compared to fossils, because fossil fuels are so cheap. But again, the idea is that we're running out of fossil fuels, whether we like to admit it or not. We are going to run out. So if we figure out ways to get ahead of the curve, which might have higher costs now, then the idea is that whatever fossil fuels we have that we'll need to continue to survive, we're not draining that to the level we would do if it wasn't for the fact for renewables. But wind, solar, all those ones probably have a higher cost than just about any fossil arena that you would see. So that's kind of, that's where the research has to happen. So.
I've been doing some research on this. Out of all the alternative energies, onshore wind turbines are the single cheapest in terms of dollar per kilowatt.
Right. So the comment, go ahead, sorry.
It's actually cheaper to build a wind turbine per kilowatt than to keep a coal plant running.
Right. So the comment is it's actually cheaper to get a wind turbine up and running than to keep a coal plant online. But I don't know if...
The downside is that each wind turbine needs about a half a square kilometer of space.
Yes. So it needs about, depending on the size again, but each wind turbine needs about half a kilometer area of space to do that. So yes, power densities aren't nearly the same as they are when you've got, a gallon of gasoline's got a lot of joules in it. The wind, doesn't have the same level. If you think about a gallon of gas and how far or how much energy you get out of it, but it's taken millions of years to get that energy density. So we don't have the same time frame or time horizon to do that. So, all right, thank you very much, and I'll see you next week. Take care.